Alright, what we're going to be talking about today are acids and bases and the different definitions we've had for those terms over the years and how we define them now and why they're important. Alright, so first of all, just general properties of an acid. You guys have all run into acids in your everyday life, whether you know it or not. Some properties of them are they taste sour, they conduct electricity very well, they're corrosive, so that means they can break down certain substances, like they can dissolve uh, fabric and skin and paper, and even the stronger ones can dissolve like plastic. Um, some of them, not all of them, but some of them will react strongly with metals as well and cause those metals to oxidize very quickly. And then if we're using litmus paper, an acid will turn blue litmus paper from blue to red. Okay, you can see over here some of the more common ones that you guys might have run into in everyday life. Acetic acid or ethanoic acid is a big part of vinegar. Carbonated drinks have what's called carbonic acid in them. Teas have tannic acid. Absorbic acid is another name for vitamin C. And then pretty much all citrus fruits and sour candy and stuff like that has citric acid in it. So again, that's kind of the same thing on this slide. I'm just going to list all those again. And then the more intense acids, your hydrochloric acid is actually part of what's in your stomach acid. And then sulfuric acid is used when they make steel and paint and fertilizer and a bunch of other like industrial products. And car batteries, part of their chemistry that makes them work and create that electricity, is a very strong acid inside of them. Okay, the other side of the coin, we have bases, which are the other half of what we're talking about in this unit. So bases, if you feel a liquid that is alkali or basic, it's going to feel kind of slippery and slimy. They taste very bitter. The strong ones can also be corrosive, so they can also dissolve or burn your skin, as well as dissolving other materials. And they also cause water that they're in to become conductive. They can conduct electricity as well. Unlike the acids, they don't react with metals. And then if we're trying to test whether something is basic, we will use red litmus paper, which when it comes into contact with a base, it turns blue. Alright, some common bases and uses of bases that we see all the time. A lot of different cleaning products and soap, detergents, laundry soap, dish soap, all that. They get their useful properties because they are basic. Bases generally have OH ions in them, which is what causes them to be able to bond with the dirt and the grease and all that and remove it. Some common ones are chalk, baking soda, and drain cleaner are ones that you might see and find around your house. And then even, like we said, we had stomach acid or hydrochloric acid in our stomach acid to dissolve food. Well, your blood is actually an example of a base. It's a slightly basic solution. Okay, so there's been a couple of different ways that we tell these things apart over the years. The first real kind of systematic definition we had for them was created in 1884 by a guy named Arrhenius. I don't know his first name, that was his last name. And he said that an Arrhenius acid is any compound that when you dissolve it in water, it increases the concentration of H plus ions that are present. So it releases those H plus ions when you put it in water. And he said an Arrhenius base is anything that does that same thing, but by releasing OH minus ions. So anything that creates H plus ions or protons is an acid. Anything that creates OH minus ions is a base. That was his definition, and it worked pretty well, right? Generally, if you find something that creates H plus ions, it is going to be an acid. And if you find something that creates OH ions, it is going to be a base. He was right about that. The issues with that come into play when you start thinking about things that don't do that but still have properties of acids and bases. So his idea was right, it just didn't include all the possibilities. And it only really worked when things were being dissolved in water. If you had acids that were dissolved in a different solvent like alcohol or toluene or anything like that, his definition, it kind of didn't hold water there. All right, so some examples of that. Typically, you're going to be able to see the H bonded with some kind of nonmetal anion. So here we have hydrochloric acid, so it's an H and a chlorine, HCl. And then when it gets dissolved in water, it creates that H plus as the cation and the Cl minus as the anion. Okay, so that's for an Arrhenius acid. An Arrhenius base, generally it's just going to be some kind of metal cation bonded with an OH. Right, so these two, they're real easy to tell apart. If it's got an H in it bonded with a nonmetal, probably an acid. If it's got a metal bonded with an OH, probably a base. Right? You can see here it splits apart into that metal cation and the OH anion. Okay, eventually though, someone came along and was like, I don't really like that definition. There's a better way to do it. And so a new classification system was developed in 1923, and it kind of solved those issues that we talked about from the Arrhenius acid and base definitions. The guys that came up with this were Bronsted and Lowry, and their definition was any substance that donates or loses a proton in a reaction is an acid. Okay, so it doesn't have to be dissolved in water. All it has to do is lose a proton or an H plus ion in a reaction, and that's an acid. And then instead of defining the bases as things that create OH minus ions, he said whatever is taking that proton and accepting it is the base. So this is a broader definition. Generally, everything that is included in the Arrhenius definition also works here. So if it's an Arrhenius base, it's going to be a Bronsted-Lowry base as well. This just kind of expands it and lets you include more things in the acid and base categories. Okay, and we'll see a little definition or a little example on the next slide, or the slide after this one actually, of exactly how that works. But along with this, we have what's called conjugate acids and bases. So this is part of Bronsted-Lowry's theory, and he said that when the Bronsted-Lowry acid donates that proton, it gets rid of its H plus, then it becomes a conjugate base because it can then accept a proton to go back to being that acid. Same thing the other way around. If you have a base that accepts a proton, so it gains that extra proton, it is now a conjugate acid, because if the reaction went the other direction, it would be donating that proton to go back to being the base. Alright, and that's a little bit confusing, but hopefully we'll look at this little example of it down here and it might make a little more sense. So right here we've got NH3, ammonia, or ammonium, I can never remember which is which, it's one of those. And it is going to be gaining an electron, or gaining a proton, sorry. It goes from NH3 to NH4 plus. So this extra H plus that got attached to it means it is accepting a proton. So that makes it a Bronsted-Lowry base, right? We said on the previous slide, if it accepts a proton, an H plus, it is a Bronsted-Lowry base. Okay, so the NH3 is what is accepting the proton. It's the Bronsted-Lowry base. That means its counterpoint on the other part of the reaction is the conjugate acid. Because if we did this reaction the other way around, it would be giving up that proton to go back to being NH3. Okay, same thing if we look at the water. Right here it's H2O. It loses one of its hydrogens, so it's giving up that proton, which makes it the Bronsted-Lowry acid. It creates the OH minus, and then if we were doing this the other way, and the OH minus is going back to being the H2O, it would be getting that proton, right? Taking it back to come back to being H2O. So the thing that would be accepting a proton going the opposite direction would be the conjugate base. Okay. It's kind of an odd concept, but if you think about it for a while, and we'll look at other examples, and hopefully it'll click eventually. Alright, so here's another example here. We've got H2SO4 as our Bronsted-Lowry acid, and what it's going to do is give a proton to the water. Alright? So if it is donating that proton or giving it up, that makes it the Bronsted-Lowry acid. And the water is what's accepting the proton, so it is our Bronsted-Lowry base. Alright, so that's what's going on this left side of the equation. On the other side, the HSO4, after it has lost that proton, if we were going to go back the opposite direction, it would need to take that proton back and accept it. So the HSO4 is what's called the conjugate base. And then the H3O, after the water has accepted that proton, if it wanted to go back to water, it would have to give that proton back away. So it's the conjugate acid. Alright? Basically, whatever was the Bronsted-Lowry acid, its counterpoint on the other side is the conjugate base. And whatever was the Bronsted-Lowry base, its counterpoint on the other side is the conjugate acid. Alright? And then we call that combination of the two things a conjugate acid-base pair. Okay, you might notice here on these two slides, this first one we talked about, we said that our water here was actually acting as an acid. And then on this one, we said our water was acting as the Bronsted-Lowry base. So, how can that be true, right? It can do both things. So that is one really cool thing about water that makes it kind of unique, is that water is amphoteric, right? There are other substances that can do this, but they're not very common. Amphoteric just means it is capable of accepting or donating protons. It can act as either an acid or a base depending on what else it is reacting with. So when the water reacted with the NH3, it was acting as the acid. And when it reacted with the sulfuric acid, it was acting as the base. So the water is amphoteric. Alright, and that's where we are going to stop our lecture for today, and we'll talk about the pH scale next time.